All right, gang, stat 1150. You'll have to excuse my voice today and all the sniffles. I've got something going on, and I can't get rid of it. I don't know what's happening. What I want to do today in this video, or at least the next maybe couple of videos, is look at confidence intervals for means. Now, we've done so far confidence intervals for proportions. So essentially, when we have categorical variables, we're going to do confidence intervals for proportions. And these things are typically illustrated by percentages. You know, what percentage of voters in the recent election, what percentage were female? Well, it's categorical because our measurement is either male or female. Well, this would be appropriate for addressing that issue. But in this illustration, this video, I want to focus from categorical to quantitative. So what we're going to look at here is confidence intervals for means. Okay? So what was the average age of voters, say from Scioto County in the last presidential election? Well, the average indicates means, and that would be quantitative because age is, of course, a number. All right, gang. Hardest thing is knowing where to get started with this. I want to revisit just a little bit the central limit theorem. But even before I get into that, I want to go back a little bit more. The overarching goal, I do believe, and I've only taught this class, gosh, I don't know, 100 times or something, is to examine this relationship between samples and populations. Population is the entire group of subjects, elements, dogs, cats, trees that we want to get more information about. The sample is a subset of the population, and in statistics, we seek a random sample. Now, we don't always get that, but studies are the best way to reduce bias, and bias is just a deviation from the truth, is to collect a random sample from the population. Now, one direction that we examine in statistics is this direction, where we start with a population and we want to determine the likelihood of getting a particular sample from that population. And that branch of statistics is called probability. So we start out in probability that our population is known, but what we get from it at random is unknown. But we'd like to calculate the likelihood or the probability of getting a particular sample value. Now, typically we phrase these questions as the probability of getting a value or higher, the probability of getting a value or lower, but it doesn't have to be that way. For example, let's say my population is flipping a coin. So I know the only outcomes are heads or tails. If I flip my coin once, what am I going to get? Well, I don't know. But I can determine the probability of getting a head. Same thing. If I roll a die, I know what my die looks like. It's got 6 sides. But if I roll it against a wall, what number is it going to land on? I don't know. It's a random variable. That's unknown. But I can determine the probability of getting a particular side. Well, guys, probability is really cool. This is not a class in probability, so we don't get into it much. But what we do get into is the opposite direction. And the opposite direction is where we take a random sample and use it to make a statement or an estimate of a population value. And guys, this is called inference. It's called inferential statistics. Now, what happens here is the known, oh gosh, the known and the unknown are switched. Here we start out with a sample. We collect a sample from a bigger population, and we're going to use it to estimate an unknown value from a population. Okay, what was the average age of voters in Scioto County in the recent election? Well, I don't know that. But if I wanted to estimate it, what I would do is I would go take a random sample, which I would clearly know because I just collected it, and I would use that to make an inference of the unknown value. So guys, that's what we're going to do. We're diving into this whole inference thing feet first, as we did with the confidence intervals for proportions. Now, before I'll tell you what, I'm hesitant. I don't. I've already taught you all the central limit theorem, and I don't want this to turn into a central limit theorem video. But it's hard to really set the framework, the foundation for confidence intervals without the central limit theorem. So let's just revisit it just a little bit. The central limit theorem and I'm not going to get into this a lot. I'm just going to kind of skip through it because I've already put up, I think one week I put up 5 videos on the central limit theorem. And guys, I want to focus on the means central limit theorem right now, okay? So the very first thing that we do with the central limit theorem is we start or begin with a population where mu and sigma are known. Okay, second thing we do is we take random samples. And we want to set our sample size, and let's just say n. Now, just for the illustration here, let's just say that n is 42. So I'm going to speak this through, setting n at 42. It could be 50, it could be 60, it could be 13,000. I'm just going to speak it through with 42. So I go into my population where the mean and standard deviation are known. I pull out 42 measurements. I add those 42 measurements up. I divide by 42. And I get my first sample mean of size 42. Throw those folks back into the population. I close my eyes. I pull out 42 more measurements. I add those 42 up. I divide by 42. I get the second sample mean of size 42. I do that again. I do it again. I do it a 5th time. I do it a 1,000,000th time. I imagine in theory doing that forever. When I do this forever, I've got new measurements that have been taken from this original population. These things are called the distribution of sample means. Central limit theorem tells us 3 really important things about the distribution of sample means. These things will be normally distributed. Now there's some conditions up here. We have to have a large sample size of 25 or 30 or more, and we draw from a population that's normally distributed. But with all the conditions met that I've explained in previous videos, we end up with a distribution of sample means that is normally distributed, has a mean. Now guys, this notation is a little wacky. It just says the population mean of all these sample means. So if I take that number, plus 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 all those numbers in that one, and divide by a lot, I'm going to get the same value that I started with way back here, that I drew these measurements from. And the second thing we know is that the variability in this distribution is explained by the standard error. This population standard deviation that we started back with in the original population, from which we drew these sample means, the variation in this distribution, not this one, but this one, we have to take the original population standard deviation divided by the square root of n. All right? So what we know is, if we go back to what we're talking about right here earlier, we start with a population, we can determine the likelihood of getting a particular sample using the central limit theorem. But guys, we're old pros at this, right? We want to shift our attention to this, and what's known and unknown completely changes. In this situation, we know our random sample, and we're trying to estimate a value from the population. Now, let's go back to the central limit theorem. So, we know that the distribution of sample means will be normally distributed. That's an ugly distribution, but pretend it's pretty, okay? And we know it's not, because central limit theorem tells us that. We know the center of the distribution is going to be mu. And we know that the variation around the mean is going to be described by the standard error. So we know that from mu minus 2 standard errors to mu plus 2 standard errors above the mean, that we have approximately 95% of our distribution of our sample means to fall in there. Now, is it really negative 2 to positive 2? Because since the first day I taught you normal distributions, I said that approximately 95% of our sample means, approximately 95% of our distribution in measurements in a normal distribution are between 2 standard deviations below and 2 standard deviations above. But guys, we're moving into big boy, big girl stuff now, so let's see if we can get a better approximation. Now, 2 isn't bad. You know, it's really not. I mean, we can go from, in the standard normal distribution, we can go from negative 2 up to 2, mean 0, standard deviation 1. And we can see this 0.95449986. Okay, not bad, but can we make it better? And my claim is we probably can. Well, I know we can, because I've taught this class before. So between what two values is a better, between what two z-scores is better to describe the middle 95%? Well, guys, think about it. We've got 100% underneath the curve. We got 95% between here and here. We're missing 5%, aren't we? So because of symmetry, we know that half of that 5% has to go here, and half of that 5% has to go here. Now, we got a handy-dandy calculator key that finds the value from a distribution when we have a percent below. It's called inverse norm. So if I put in the decimal equivalent with a mean of 0, standard deviation of 1, I see that negative 1.96 is better than 2. Because of symmetry, positive 1.96 is going to be better than positive 2. So guys, what we can say is we can say that between again, we get the mean in the center. We want to focus on 95%. I had a student ask me one time, say, Dr. Darbro, what's so holy about 95%? I have no idea, but it sure does pop up a lot in statistics, especially with confidence intervals. So with this distribution of sample means, we know that from mu minus 1.96, standard deviation over the square root of n, to mean plus 1.96, standard deviation over the square root of n, that 95% of our sample means will be between here and here. All right, let's change gears. Mean is unknown. So we're switching gears and we're coming back to that original drawing, and we're switching directions. No longer looking at the probability of something unknown. We want to go this way. And the foundation of this is that the mean is unknown. I'm sorry, the mean is known, but the population value is unknown. So this is unknown. And we come in here and we get a sample mean, and let's just say it's that one right there. All right? I want to know how well this approximates that value. I want to create an interval that hopefully, if things work right, you never know, creates that value. So what's this interval going to look like? Well, guys, if I move this over, so let's move this over and center it around this, then I am going to get an interval that's going to be built right there, but it's centered around my mean, which I know because I collected it. Will it collect, or I'm sorry, will that interval contain the population mean? Well, the way I drew it here, it will. But what if I just happen to randomly get this one? Well, if I take this and build it around this value, you can't see my hand, just trust me, it's over here. Notice that the mean that we're trying to estimate is not contained in that interval. But we know that 95% of our means are between here and here. So if we choose one at random, there's a 0.95 probability that we get a mean between here and here, whereby if we build an interval around it, it's going to contain what we're looking for. So guys, that's the foundation between what we call a confidence interval. So the center of this interval, let's just focus on this thing right here. And then we'll come over here and focus on this one right here. What does this value right here look like? Well, it's the sample mean minus. This value right here was just moved over, wasn't it? Not centered around mu because that's unknown. Centered around x bar, that's what we collected. So it's just this shifted over. What's this look like? Well, it's just this shifted over, but it's not centered around mu, it's centered around x bar. So we have the same thing, just a plus and minus. Giving us this. Now, I'm getting ready to end this video pretty quickly. Let's think how realistically this is likely to happen. The population mean is unknown, but we just magically happen to know the population standard deviation. So we're using a population standard deviation to estimate a mean value. Now, does this ever happen? It does. Is it likely? It isn't. Typically what happens is sigma is also not known. So how can we use it in our calculation of the estimate of mu when chances are it isn't known as well as not knowing mu? Well, in the next video I'm going to address that. What do we do when the population standard deviation also isn't known, which is typically the case? Okay?